Hi, my name is Noah Petro. I'm the project scientist for NASA's Lunar Reconnaissance Orbiter, a mission that we've had orbiting the moon now for over 11 years. I'm going to talk to you today about our data, what we've learned about the moon, and why the moon remains a compelling target for human and robotic exploration. But I'm doing so over a video that we released earlier this year to celebrate the 50th anniversary of the Apollo 13 mission. What you're seeing is the view that the Apollo 13 crew had as they circled behind the moon on their trip back to the Earth. This is a view that only they could enjoy. And of course, while they were in their powered down spacecraft, they spared few moments to look out the window. While they captured some images, this is a view that only they have ever enjoyed. And so I think it's appropriate that we tag along with them and look at the far side of the moon. When LRO got to the moon in 2009, our view of the lunar surface and its environment was heavily colored by the Apollo exploration of the lunar surface and by the subsequent missions that orbited the moon. But of course, those missions only lasted from months to just a few years. And so now, with a decade plus of observations from LRO, we're able to understand the dynamics of the moon, how it changes and evolves over human timescales. The views of the moon that we get from LRO show us a dynamic, changing environment. We find new impact craters, we see landslides, and indeed we see how volatiles may migrate across the lunar surface as a function of time of day. The sunrise that the Apollo 13 astronauts observed over the lunar surface shone a light on the far side of the moon. Of course, this hemisphere of the moon has never seen the Earth, but it reveals the scarred ancient traces of impact craters that bombarded the lunar surface early in its history. Of course, these impact craters not only hit the lunar surface, but we know that there are a number of impact craters that formed on the Earth as well early in its history. And so we use the moon as this witness plate for processes in the solar system, from those that occurred billions of years ago to the ongoing processes that occur as we speak. One of the most indelible marks on the lunar surface are not only these large basins and large impact craters, but indeed features at the scale that we can't see with our own eyes. The LRO spacecraft is able to record the radiation environment at the lunar surface or in lunar environment. We're able to understand how humans will respond to extended periods of time at and near the moon. And so in this way, we're paving the return to the moon, not just with incredible data for the lunar surface, where we want future explorers to visit, but also what they can experience when they're at the moon. And so in that way, we're buying down risk for our future explorers. Of course, we anticipate crew and rovers and robots exploring the lunar surface, but also a number of astronauts will be observing the moon from above, from high over the lunar surface, from either the gateway or from orbital assets. And so what we do with these data that we've created is understand what the moon will look like at a variation of scales. Here we see the far side from above. And again, using data from our laser altimeter, we get the precise shape of the lunar surface. We can understand the color and composition of the moon thanks to our Lunar Reconnaissance Orbiter camera. We also can get thermal properties, the temperature extremes that cycle through day-night to understand how the surface will respond to varying illumination conditions. All of this data helps us better understand what our future explorers will endure while they're on the lunar surface. Now, of course, these images showing the far side, and here we have Tsiolkovsky crater, a beautiful Mare-flooded, relatively young, only a few billion-year-old crater, basically exposes deep-seated material that have been brought up to the surface. But what we like to do with our data is try to understand and unravel the geologic history. Of course, what we're seeing here are features that are near and around the lunar equator. Our future explorers may be going to the lunar poles. The craters that they'll be exploring are not things that we'll be seeing like this. The craters may be much smaller, but what we'll see are features at the scale of smaller features, craters that we can barely see, for instance, in this visualization. But we know the importance of the cratering process, and we know that by studying large features such as Tsiolkovsky, we can answer questions about the fundamentals of how craters are formed by exploring smaller and smaller features at the scale that a human astronaut explorer may actually venture into and explore near the lunar South Pole. Of course, the Apollo 13 astronauts, as all of the Apollo crews enjoyed, was the view of the Earth rising above the limb. And I think it's really important to remind ourselves that anytime we think of lunar science and look at the moon, we're actually looking at a window into the Earth's ancient past. And so I always like to think of the moon as an extension of the Earth and actually a perfect companion of ours in deep space. When we study the moon, we look back to the processes that occurred billions of years ago, early in Earth's history, but also the processes that occur today. But because of our atmosphere, because of our magnetic field, processes that don't occur on the Earth's surface. And so the moon provides us incredible opportunity to understand the fundamentals of planetary science, essentially in our very own backyard. And so as we prepare to return to the lunar surface with robotic and human explorers, I think it's important to understand how these perspectives of the moon will inform our understanding of the entire history of the solar system, not just of the history of the moon, but indeed of every solid body in our neighborhood. Indeed, our understanding of how planets form is largely informed by our thoughts on how the moon formed and how its crust formed early in its history. When we observe planets orbiting other stars outside of our solar system, our understanding of how those objects are potentially forming, those planets are forming, is largely informed by our understanding of how the crust formed, or how we think the crust on the moon formed. The orbital data from LRO gives us a global perspective of the composition of the crust, its variability, and what that might mean for how the crust of the moon formed over 4.5 billion years ago. As the Apollo 13 crew left the moon, they were treated to breathtaking views of some of the large basins and the large impact craters. This is a perfect example of how the moon and its surface bears witness to over 4.5 billion years of history. And that first step by astronauts in the 21st century on its surface will build on the legacy of Apollo, but also start its own legacy. The legacy of Artemis is going to be written in the coming years by a generation that was not alive during the Apollo exploration of the moon. And in doing so, we'll set forward on a path to explore deeper into the solar system. The volatiles that we may find at the South Pole in the form of water and hydroxyl may be used for fuel, for materials to build long-term habitation on the lunar surface. Indeed, the moon will serve as our stepping stone deeper into the solar system and beyond. Thank you for your time today. I hope you enjoy the rest of AGU 2020, and I'll look forward to seeing you all soon. Thanks very much.